Okay, welcome Mathcounts friends. Today we are looking at the 2025 school target round. So let's go ahead and jump right in with problem one. So problem one says Bob gets paid $16 per hour for the first 40 hours and $24 per hour for each hour after the first 40. If Bob worked 55 hours, how much does he get paid? Okay, so we're allowed to use a calculator, so we might as well do so. I can't show a calculator on screen, but I can show you Python. And basically this is pretty simple. You take $16 per hour times 40 plus $24 per hour times the number of hours he worked beyond 40, which is 55 minus 40, which is 15, and that gives you $1,000. So the answer here is $1,000. Whoops, $1,000. Okay, let's move on to the second one. Usually the odd problems on a target are a little bit easier than the even ones, but sometimes that's not the case. This is problem 2. It says how many permutations of the digits in the number 1, 2, 3, 4, 5 have all odd digits adjacent and all even digits adjacent? And then they give you one example. One permutation to include is this number here, 5, 1, 3, 4, 2. You can see that the first 3 are all odd, and then the last 2 are all even. Okay, so how are we going to do this? First of all, we have to realize that the odds going together and the evens going together means you can either have the odds first and then the evens, or you can have the evens first. There's 2 evens, and then the 3 odds afterwards. So that's 2 different possibilities. But we also have to consider how many different ways there are to arrange the evens within this box and how many different ways there are to arrange the odds within this box. So we're going to multiply those all together. So there are 3 factorial ways to arrange the odds. There are 2 factorial ways to arrange the evens. And then there are 2, factorial ways to arrange the 2 blocks. So this gives us 6 and 2 and 2, and we just need to multiply those all together, and that gives us 24 in total. So that's the answer to number 2. All right, let's take a look at number 3. So this one says, what is the sum of all distinct values of the expression x minus yz, where each of x, y, and z is one of the numbers, and then they give you a list of 3 numbers, and no 2 variables share the same value. Okay, so we've got x minus yz. Now, it doesn't matter, once you pick x, it doesn't matter which of the 2 remaining you call y, because the other one's going to be z, and when you multiply the 2 together, you're going to get the same result. So that means once you've picked x, you have fixed the value, and all we care about is the value. So we're not going to count it twice. If you pick, for example, if you pick negative 2 to be x, let's just write that one out. You get negative 2 for x minus yz is going to be 5 times negative 8, right? So it doesn't matter whether you pick 5 to be y or negative 8 to be y, this product is going to be the same, and it's going to give us the same value. So we can just think about the 3 possibilities for what we choose for x. This is 1. The next one is to choose 5 for x, which gives us y and z being negative 2 and negative 8, which gives us 16 for the product. And then negative 8 for x, we're going to subtract the product of negative 2 and 5, which is negative 10. And so basically we just have to add these things all together. If we add these first 3 here, we get negative 5. And then these ones, let's see, let's write them, maybe I'll write this whole thing negative 40, that's just going to be 40. And the negative 16, and then this is negative 10, that's just going to be 10. So we have 50 minus 16, that's going to give us 34. So now we add these 2 together and we get 29 as our final answer for this one. All right, let's go ahead and move on to problem number 4. This one says at Southern Unified Middle School, SUMS, each student is taking algebra, geometry, or both. Okay, so that sounds like a Venn diagram problem. I'm going to go ahead and draw a Venn diagram with algebra over here and geometry over here. And this first sentence told us that all the students are somewhere inside here. There aren't any that are taking neither one. They're all either taking algebra or geometry or both. And it says the total enrollment in algebra class is twice that of geometry class. So that means everything inside this circle, all the students inside this circle has got to be twice as many as the number in this circle. Okay, so if I call this x and this y and this z, for example, that's saying that x plus y is equal to 2 times y plus z. And then it also says that the number of students not taking geometry, okay, that means x plus, oh wait, we already did that one. Total, oh, the total number of students not taking geometry. Oh, that's the same thing. That's x plus y, right? It's got to be equal to, hang on, did I do this right? The total enrollment in algebra class. Oh no, the number not taking geometry is just x, my bad. The number not taking geometry, that's just x. So the number not taking geometry is 4 times the number not taking algebra. Okay, so that's equal to 4 times z. Okay, so we can plug in 4z for x in this expression up here. Let's just do that. Then we don't need that equation anymore, I think. So this x is now 4z. And now we have 4z plus y equals 2y plus 2z. So this is equal to 2y plus 2z. All right, so we can subtract 2z and y from each side. So that's going to give me 2z is equal to y. All right, so now I know that 2z is equal to y. So let's replace y by 2z. And I think we had said before that x was equal to 4z. So let's do that. Let's replace x with 4z. And now we have everything we need to answer the question. The question is, what fraction of the students at sums are taking both algebra and geometry? So that's 2z out of the total, which is 7z. So the fraction is 2 over 7. And that's our answer to that one. So we can never actually solve for all of these. We never actually know the number. We never solve for z or x or y because we had two equations and 3 unknowns. So we weren't actually able to solve for the actual numbers, but we were able to see the proportions between these different quantities here. And that's all we needed in order to find that ratio that they wanted. Okay, now let's go ahead and take a look at problem 5. This says, how many different possible integer values are there for the mean of a set of 3 distinct positive integers, the greatest of which is 50? Okay, so one thing I like to do in this case is think about what is the biggest possible mean that I'm going to be able to get, and what is the smallest possible mean. So if I want to make the mean as big as possible, I'm going to want the numbers to be big. We know they're integers, and that the biggest one is 50. So the biggest I'm going to be able to get is if I have 48, 49, and 50. And of course the mean there is 49. That's going to be my biggest mean that I can possibly get. Now what's going to be my smallest mean that I can possibly get? My biggest value is still got to be 50, but I want to make it as small as possible. And it says that these are distinct positive integers. So because they're distinct positive integers, 1 and 2 is going to be the smallest I can make them. 1 is the smallest positive integer, and the other one has to be distinct from that, and so the smallest I can do is 2. So this adds up to 53, which is not divisible by 3. So it's not going to be an integer mean, and they're asking how many different possible integer values are there for the mean. So I'm going to have to go a little bit bigger. Let's turn this 2 into a 3. Now that adds up to 54, and 54 divided by 3 is an integer. So that's equal to 18. So my smallest mean is going to be 18, and my biggest mean is going to be 49. And the only question that remains is, can I get all the numbers in between? And the answer is yes. Like, let's say you just pick a number in between, like 30. Is there going to be a way to get 30 as my mean? And of course it is, because it just means you have to make the sum 90. and it's easy to make the sum 90. It just means that those other two numbers have to add up to 40, which is very easy to do. There's many ways to do it, actually. So we're going to be able to get all the means from 18 all the way up to 49. So we just need to count how many that is, and that'll be 49 minus the 17, which are the ones before 18, right? So if you subtract these two numbers, you have to add 1 because it includes both of these, both 18 and 49. So we subtract this, and we get 32. So 32 is the number of values that you can get. That's the final answer. All right, only 2 more to go. This one says, right triangle ABC has integer side lengths. Okay. And it says the altitude from right angle C intersects side AB at point D. So that's this altitude right here. And it says the length of CD is 12. Okay, so this is 12. And then it says if the side lengths of triangles CAD and BCD are also integers, what is the minimum possible perimeter of triangle ABC? Okay, so that's pretty strict that all these lengths have to be integers because we know we've got a right angle here, a right angle, right angles here and here. And so there's a lot of Pythagorean triples that have to work out. And the first one we can look at is this 12 here. What are the possible values for a Pythagorean triple that we might have here? So if you want 12 to be one of the legs of a right triangle, that means that if we put x here and y here, that means that x squared plus 144 has got to be equal to y squared. And you probably know a few Pythagorean triples that would satisfy this. So for example, there's 5, 12, 13 is one. And there's also, you can do 12, 16, 20, where this is a 3, 4, 5 triangle scaled up, with the 3 being scaled up to 12. I'm sorry, the 4, the 3 is multiplied by 4. Yeah, the 3 is being scaled to 12. If you take the 4 and scale it up to 12, then you're going to be at a 9, 12, 15 triangle. So these are 3 different possibilities for the side lengths of this triangle ACD. And it turns out that those are also the same 3 possibilities for the side lengths of BCD. So we're getting close. And the last thing to realize here is that this triangle ACD is going to be similar to triangle CBD. And they're also both similar to triangle BCA. Or maybe I should call it ABC, but ABC is the same thing, but I'm just trying to be consistent. So yeah. So these 3 triangles are all similar to each other because they all share a common angle. This angle here, let's call it theta or something, that's going to be equal to this angle here because they're both complementary with this other angle phi over here. So this is theta, and phi. Okay, so they're all similar triangles. And what that means, if I label this thing z, it means that 12 divided by x, that's the ratio of this length to this length, has got to be equal to the ratio of z divided by 12. Z divided by 12. And that means that xz has got to be equal to 144. Okay, so what that means is we've got to find 2 of these other legs that multiply to give us 144. And the way we do that is we take 9 and 16, because 9 and 16 is equal to 144. So it's got to be these 2 triangles. And if you say ACD is the 12, 16, 20, then BCD has to be the 9, 12, 15. The way they've drawn it, it looks like the ACD is the smaller one, but you can't rely on that in Mathcounts. But it turns out if you pick one to be one, the other is the other. So maybe just to be consistent with the way they drew it here, We'll call this 9. We'll say x is 9. We'll say y is 15. Whoops. Let me fix that. 15. And then z is going to be our 16. And then this is a 12, 16, 20 triangle here. So what is the perimeter of our big triangle ABC? So we've got a 20, we've got a 15, that gives us 35. And then here we've got another 25. So 35 and 25 gives us 60 for the total perimeter. And that's our final answer on this one. Okay, let's take a look at problem 7. This one says Juno wrote all the numbers from 100 to 120. Okay, so he was writing them all down like this, and I'm not going to write them all, but he went all the way up to 120. And the question is, what is the sum of all the digits that Juno wrote? So not the sum of all the numbers, but the sum of all the digits. And I think the best way to solve this is to take each digit's place, I should say, separately. So we can start with the ones digit place. So sum up all these guys here. And what you're going to see is that you're going to start with a 0. You're going to go 1 all the way up to 9, back to 0, 1, all the way up to 9, back to 0. So we have these two sets of 1 to 9 that we have to add up. And we can say, whenever you have an arithmetic series, you can take the starting number plus the ending number divided by 2. That gives you the average number, and you multiply by the number of numbers that there are. So that's 1 plus 9 over 2 is 5, and the number of numbers is 9. So that's 5 times 9 is 45 for the sum of all the numbers 1 to 9. Or you just add them up, but that's a little bit easier. Then you get another 45 here, and so altogether you're going to have 90 for the sum of your ones digit place. Now let's go on to the tens digit. You're going to have a bunch of zeros at the beginning. Then you're going to have 10 ones. At some point you're going to have 10 ones. That's going to add up to 10. Then you're going to have a 2 at the very end. So that's 12 altogether. So we have 12 and 90. And then finally we have the hundreds place, right? So the hundreds place is all ones from 100 all the way to 120. Every single one is 1. How many are there? There are 21. You want to be careful not to make an off by 1 error there. There are 21 numbers from 100 to 120. So now we have the sum of the hundreds, the sum of the tens, and the sum of the ones. We can add those three numbers together. Let's see, that gives us 102, 103, 130, 123. 123 for our final answer on problem 7. All right, now we've got the last one, which was very tricky. Kind of tricky, I would say. This one says the figure shows 4 congruent unshaded squares. Okay, 1, 2, 3, 4. That's these unshaded squares inside a large square. Okay, so this is the large square all the way this whole distance. This is the large square here. The 9 shaded regions inside the large square consist of a small square. That's this guy. With an area of 1/4 of one of the unshaded squares. Okay, so we're told that the area of this guy is 1/4 of these guys, which means we could kind of cut these guys into 4 pieces like this. And if we did that, you would have each of those pieces being equivalent in area, equal in area to the shaded square in the middle. Okay. What else? It says 4. Oh, it says. Yeah, so that's the one unshaded square, and then, that's the small square that's shaded, that's equal to the area of 1/4 of one of the unshaded squares. And then there's 8 right triangles, 4 with area 5 and 4 with area 4. Okay, so some of these triangles are bigger than others. So for example, the ones that are completely on the edge here, they're bigger. So they're going to be 5, 5, 5, 5. That doesn't show up super well. Maybe I should grab a different color. And then these other ones are 4, 4, 4, and 4. Okay, so the question is, what is the area of a large square? So we know the area of all the triangles. We can just add that up. So we got 5 times 4 for the area of the big triangles. That's going to be 20. And then we've got 4 times 4 for the area of the smaller triangles. That's 16. So altogether we have 36 for the triangles. And now the squares. The squares well, if we cut these all up, if we cut the 4 big squares into 4 little pieces each, now we've got 17 squares. So basically the area of all the squares has got to be 17 times the area of the small square. So let's call the small square area S. So our final answer is going to be 36 plus 17 times the area of the small square. So the last thing we have to do is figure out the area of the small square. And what we can do is we can take advantage of the fact that we know the area of one of these triangles along the edge. Because if we take a look at that triangle, what we'll see is that it has some base, x, and some height, which we can call 2x, because it's 2 of these distances is the height, right? The height is twice as big as the base. And then we know the area of that thing is 5. So what is the area? The area is 1/2 the base times the height, and the base times the height is 2x squared. So 1/2 of 2x squared is just going to be x squared. So x squared is equal to 5, because we know the area of this thing is 5. So that means we can figure out x is going to be the square root of 5. And that means that one of these squares, like this central square here, which is also the same area as all these other squares, has got to be square root of 5 times square root of 5. So that area S is going to be equal to 5. Okay, so now we're almost done, because we know that our area of our whole square, the big square, is 36 plus 17s. So 17 times 5 is going to be, let's see, 85. So we've got 36 plus 85. What does that give us? This will be 110 plus 11 is going to be equal to 121. So that's our final answer. I guess that means that the side length here is 11. It's an 11 by 11 square. But what it wanted was the area, so that's 121. Okay, hope you guys enjoyed that video, and I'll see you guys in the next one.